All right, here's a problem where a half-kilogram ball is ejected from a tube at A with a horizontal velocity of 2 meters per second. Coefficient of restitution at B is equal to 0.6. And in this problem, we are trying to find a couple of things. The first thing we're trying to find is this distance R, which is included in our diagram right here. It's the distance from where it's shot out of the tube to where it lands at B. That's the distance R that we're talking about. Usually they use uppercase R to indicate range, which is what R stands for. So we want to find the range before it strikes the inclined plane, and we also want to determine the speed at which it bounces from the plane itself. So to remind ourselves what is provided in this problem, let's write down what is given. So we know the mass of the ball is equal to 0.5 kilograms. We know that the initial speed, VA, is also the initial speed in the x direction. There's no y component of its velocity initially, 2 meters per second. They say that it's launched horizontally, so we know that there cannot be a y component initially for its speed. Coefficient of restitution between the ball and the inclined plane is 0.6. And we are trying to find the distance r where it strikes the plane itself, and we're trying to find the speed VB2, I guess we can call it, the speed that it ejects after bouncing off the plane, the rebound speed after it bounces off of B. So this is kind of a tricky problem because it has a lot of different elements and it incorporates a lot of things that we've learned in this class. So to start things off, I'm going to choose a location for my origin because I recognize that to begin with, this is going to be a projectile motion problem. So as we've done in the past, I'm going to call my origin kind of at this fictitious, not fictitious, but this location within the plane itself that corresponds to the lowest position and the furthest over to the left that we're going to consider in this problem. So the horizontal I'm going to call x, of course, and the vertical I'm going to call my y direction, like so. And so by clearly indicating where my origin is for this projectile motion problem, I can immediately start writing some information down about what I know for this particular problem. I know that the initial speed in the y direction is 0. Okay, there's no speed in the y direction initially. And so I look at this problem and I say, well, if I'm trying to find, first of all, where it's going to land, this location R, I need to treat this problem initially as a projectile motion problem. So that means I'm going to write out my projectile motion equation, so my x direction and my y direction. In the x direction, I really only have one meaningful equation, which is x is equal to x naught plus v naught x times time. Now, the other x direction equation is just simply a statement that for projectile motion, without any friction, without any air resistance, the x component of the velocity of a projectile remains unchanged. There's no acceleration in the x direction. So that means that this next equation that I've written down for the x direction, x is equal to x naught plus v naught x times t. Well, according to my origin, this ball starts at a position x naught is equal to 0. It starts at x naught is equal to 0. V naught x, I'm aware of what that is. And this distance x on the left-hand side of the equation is the final location that I'm interested in. Well, it turns out I want to know r, and that's going to be equal to v naught x times t. So v naught x is 2 meters per second times time. So, well, in order for me to determine what the distance r is, I need to figure out what time it is. We've seen this 100 times already in this class. So in order to figure out the time of flight, I turn to my y direction equations and I start looking at this and I go, okay, well, this equation here, y is equal to y naught plus v naught y t minus 1/2 gt squared is a great equation to use when I want to solve for time, because I know my initial y position is equal to, well, again, according to my diagram, the ball is way up there, so it's initially at a position that's equal to, well, I guess on the left-hand side of the equation, y, where it's going to land, is 0, but its initial position is going to be equal to, well, this is kind of tricky, isn't it? Let's look at this diagram that I've drawn right over here. Okay, we know that from where it launches initially to where it lands at B looks like this. This is my x dimension, and we'll draw my y dimension in red, so it's like this. So this small distance from the top of the ramp to where it shoots out of the tube, we know is 4 meters. So it's going to start some distance x, well, I'll call this, I don't know, y1, plus 4 meters. It would be nice if I could relate y1 to this distance r, the range that it lands at. Well, it turns out that I can, because I know that the angle of incline is 30 degrees, and I recognize that tangent of 30 degrees is equal to y over r, so, or y1 over r. So the initial position of the ball is going to be equal to 4 meters, okay, that small distance, plus y1, but y1 is just simply r tan 30. The reason why I came up with this relationship was because I recognized that I have an equation in my x direction relating the range and time, and so I want a new equation that relates range and time with one another. So plus v naught yt, that's 0, minus 1/2, we're dealing with SI units, so g is equal to 9.81 meters per second squared times time squared. Okay? So now I have two equations with two unknowns. Two equations where both the range r and the time t are unknown. I'll leave it up to you to solve this system of equations, but it turns out that time is equal to 1.028 seconds, and the range is equal to 2.06 meters. Excellent. So we've solved for this first quantity that this problem asked for, the range. It lands 2.06 meters to the right of the chute that it falls out of. Okay. Now the second part of this problem asks us to determine the speed at which it rebounds off of the plane. So at this point, we recognize that we're dealing with an impact, a particular type of impact. This is called an oblique impact problem because this object, the marble or the ball itself, is striking the ground at an oblique angle, or rather at an angle with respect to this line of impact between the two objects. So if I were to consider drawing a larger diagram of what's going on here, we recognize that the ball at one point is going to be striking the ground at some angle and then bouncing off from the ground itself. And if I were to highlight the line of impact, which connects the centers of mass of the two objects, it would be this green line here, more or less. This would be our line of impact. So this object is coming in with an initial velocity before the impact, and it's going to bounce off and leave with a final velocity. So we could call this VB1, and we can call this VB2 to indicate the speed at the velocity of the ball as it approaches the ramp at location B, and VB2 would be the velocity of the ball after the impact as it departs from the ramp. So this is an oblique impact problem. It's with the Earth. Okay, so we've studied problems where we have impact with the Earth. The Earth doesn't change its velocity in any meaningful way. But of course, in order for us to solve this problem, we're trying to find VB2, meaning we need to know, if we break this down into its component form, we need to know the component of VB in the direction perpendicular to the line of impact. So VB2, call this perpendicular, and the component of VB2 that is parallel to the line of impact. So we have two unknowns, VB2 perpendicular and VB2 parallel. All right? That means in order to solve this problem, we need to determine the initial perpendicular component, so VB1 perpendicular, and VB1 parallel with respect to the line of impact. So how do we determine that? Oh, well, now the problem just got a little more wrinkly, huh? So what's happening is this ball is coming down and about to strike the ground. And we want to know its velocity just before it strikes the ground. And we can determine what its velocity is just before it strikes the ground from our projectile motion equations. Well, one of the first things that I said was there's no acceleration in the x direction. So the velocity as it approaches position B in the x direction will remain unchanged. So VB1 in what I'd call the x direction will still be 2 meters per second. VB1 in the y direction, okay, well, how do we determine that? We know the time of flight, 1.028 seconds. We solved for that previously. So knowing the time of flight, I can determine the y component of its velocity as it approaches B. VB1y is going to be equal to its initial velocity minus gt. Initial velocity in the y direction is 0, so that means VB1y is going to be equal to negative 9.81 meters per second squared times the time of flight, which we said was equal to 1.028 seconds. 1.028 seconds. That means as it approaches B in the y direction, it's traveling at negative 10.0886 meters per second. Okay, we now have the x and y components of the object's velocity as it approaches B. The problem is we're dealing with an inclined plane now. So we need to factor in the angle of the incline as it relates to the x and y directions for this ball. So if I know that VB1 in the x direction is 2 meters per second, and in the y direction it's a negative 10.0886 meters per second, its resultant velocity will be the hypotenuse of this. This is the resultant velocity, VB1, we'll call it. And I'll put a little arrow there to remind ourselves that it is a velocity by itself. Okay? So, first off, we need to determine the magnitude of VB1. Okay, what's the magnitude of VB1? It's going to be the square root of the sum of the squares. So VB1 has a magnitude of square root of 2 squared plus 10.0886 squared. The magnitude of VB1 is equal to 10.285 meters per second. This represents the speed at which the ball is traveling as it approaches B. This is the speed that the ball is traveling as it approaches B. However, when we go back to this diagram, the speed VB1 is right here, this red. Okay? However, we need to know its angle with respect to the incline as it's approaching the incline. Kind of interesting. How do we determine that angle? Well, I can determine this interior angle, call it theta, or call it phi, so we don't get confused with thetas that are used later. So if I call this angle phi, I know that angle phi is going to be equal to the tangent of opposite over adjacent. So phi is equal to the inverse tangent opposite over adjacent, 10.0886 divided by 2. I find that this angle turns out to be 78.8 degrees. Okay? So this ball is traveling 10.285 meters per second at an angle of 78.8 degrees with respect to the horizontal. Opposite interior angles tells me that this must also be 78.8 degrees. So the ball is coming down at an angle of 78.8 degrees, and it's going to strike an inclined plane that's inclined at 30 degrees. So let's try and draw this and visualize what's going on here. So if I have an inclined plane that's at 30 degrees, not to scale, and I have a ball that's coming down and going to strike it and then bounce off, and I know that this angle is 78.8 degrees, because I know with respect to the horizontal, as I said in the previous one, 78.8 degrees separates the velocity vector with the horizontal as it approaches. Then I know the angle with respect to the incline is 48.8 degrees. This is all just from geometry itself. Takes a little thinking. I don't expect you to just see this immediately, but replay this video as many times as necessary. That means 48.8 degrees is the angle at which this ball is approaching the surface. Now we have enough information to determine the components of VB1 in the parallel and perpendicular directions. Okay? This 48.8 degrees is the same as this angle here, 48.8 degrees. I've drawn in green. So if I wanted to know the perpendicular component of VB1 perpendicular, that would be equal to VB cosine 48.8 degrees. VB1 parallel, that would be equal to VB sine 48.8 degrees. So this is an oblique problem, an oblique impact problem, and we recognize from practice and from our derivation that the velocity of the ball in the direction that is perpendicular to the line of impact, VB1 perpendicular, will remain unchanged through the impact. VB1 perpendicular and VB2 perpendicular are exactly the same. So VB1 perpendicular is equal to VB2 perpendicular. And this is going to be equal to VB cosine 48.8. VB cosine 48.8 degrees. Or this is VB1, the approach velocity. And we know what VB1 is because we solved for its magnitude, 10.285. 10.285 meters per second cosine 48.8 degrees. Therefore, VB2 perpendicular turns out to be 6.77 meters per second. VB2 perpendicular is right here, circled in red. So that gives me one component of the final velocity after it bounces off the inclined plane. I still need to determine VB2 parallel. To solve for VB2 parallel, this is where I finally invoke my coefficient of restitution. I consider two objects. Object A, I'm going to call the ball. Object B, I'm going to call the Earth, or the plane itself. My coefficient of restitution is defined as the relative velocities of the two objects after the collision occurs. So VA2 in the parallel direction minus VB2 in the parallel direction. I guess I'm mixing up my notation here. But in this case, I'm talking about VA2. This would be the final velocity of the ball, which now I'm calling A. I recognize that might get a little confusing. Minus the final velocity of object which I call B, which is the Earth, after the collision occurs, in the parallel direction, over VB1 in the parallel direction minus VA1 in the parallel direction. So this corresponds to the ball, the velocity of the ball in the parallel direction after the collision occurs. This corresponds to the Earth, the velocity of the Earth in the parallel direction after the collision occurs. And again, this would be the Earth before the collision occurs in the parallel direction to the line of impact. And this would be the ball in the parallel direction with respect to the line of impact. Well, the Earth doesn't change its velocity in any meaningful way, so those just go to 0. And we find that VA2 parallel, okay, this is the velocity of the ball, the component that's parallel to the line of impact after the collision occurs, is equal to the coefficient of restitution times negative VA1 parallel. Well, I never defined my positive and negative direction in the line of impact, but if I call positive in my parallel to line of impact direction positive away from the surface, then we recognize that as the ball is approaching the surface, it would have a negative component of its velocity. As the ball bounces after it collides with the Earth, it's moving up with respect to the surface, so it would have a positive line of impact, positive along the line of impact. So before the collision occurs, we'd have VA2 parallel is equal to the coefficient of restitution 0.6 times negative VA1 parallel, which was the velocity of velocity of the ball as it's coming into the ground, coming into the ramp itself. This was negative 10.285 sine of 48.8 degrees. So these negatives cancel out with one another. We're left with VA2 in the parallel direction is equal to 4.64 meters per second. So their problem is asking us for the final speed after it bounces off the ground. So the final speed after it's all said and done is going to be equal to VA2 parallel plus VA2 perpendicular. Square both of these, square root. So V is the square root of the sum of the squares. So this is the square root of 4.64 squared plus 6.77 squared. So the final speed here turns out to be 8.21 meters per second. Tricky bird. We had to use our projectile motion equations to determine the speed of the ball as it approached the ramp. Once we determined the x and y components of the object's velocity as it approached the ramp, we could then determine the angle at which it was traveling just before it strikes the ramp. And then with respect to the incline angle of the ramp, we could determine the angle at which it was approaching the ramp and resolve the coordinates into our line of impact, our parallel line of impact direction, and our perpendicular to line of impact direction. Okay. So when we're dealing with oblique impact, we study it from the perspective of the momentum that's directed along the line of impact, and from the perspective of the momentum that's directed along a line that's perpendicular to the line of impact. And we use the appropriate equations to solve from there.